Welcome back. Today, we're jumping headfirst into the world of advanced IP address subnetting. And look, I know that can sound a little dry, but I want you to think of it differently. This isn't just about numbers. It's a quest for perfect network efficiency, a puzzle where the goal is to not waste a single precious IP address. Let's get started.
All right, to really get our minds wrapped around this, let's kick things off with a huge, real-world challenge. Picture this. You are the chief network architect for some massive global company. You've got 2,000 different departments, and every single one needs its own unique network space. How on earth do you make that happen? That's exactly the kind of problem we're going to solve today.
So first up, we're going to scale up our thinking. We'll start by wrestling with a problem of enormous size. Why? Because it's the best way to really nail down the core concepts before we get into the really slick, elegant solutions. Okay, let's do a quick warm-up. If you remember from our last explainer, we looked at a classic scenario, taking a 16 network and carving it up. The correct answer there was a 23 prefix, which gave us 128 subnets with 510 hosts each. So with that fresh in our minds, let's really turn up the heat.
And now for the main event, subnetting a Class A giant. Seriously, we're talking about a network with millions upon millions of potential addresses. This is where the real fun begins.
Here it is, our mission. We have this enormous 10.0.0.0/8 network block. Our job is to slice it and dice it into 2,000 separate subnets for all those departments we talked about. The scale here is just massive, so every single choice we make is critical.
So where do we even begin? Well, the first step is always to figure out how many bits we need to borrow from the host part of the address. We need 2,000 subnets, so we ask ourselves, what power of 2 gets us there? 2 to the power of 10? That's 1,024. Not quite enough. So we go to the next one up. 2 to the power of 11 is 2,048. Perfect. That's our number. We need to borrow 11 bits.
So what does that do to our network? It's actually pretty simple. Our original network prefix was a /8. We just borrowed 11 more bits for our subnets, so we add them together. 8 plus 11 gives us a brand new prefix of /19. This gives us our 2,048 subnets. But what does that leave for the hosts inside each one?
That's how many? 8,190 usable host addresses in every single one of those 2,048 subnets. I mean, that is a ton of addresses. It's powerful for sure, but it raises a really important question. Does that tiny 10-person accounting department really need over 8,000 IP addresses? Absolutely not. And that leads us to a really big problem.
This really gets to the heart of the issue, the one-size-fits-all approach. When we give every single department, whether it's huge or tiny, a massive /19 subnet, we are being incredibly wasteful. There has got to be a smarter way to do this.
You know, what we've been doing so far has a name. It's called Fixed-Length Subnet Masking, or FLSM. And you can see it's easy because every subnet is identical. But its big weakness is that it's just so wasteful. But on the other side, we have Variable-Length Subnet Masking, or VLSM, and this is the hero of our story today. It's flexible, it's efficient, and it gives each network the exact size it needs.
Just take a look at this network diagram. It's a perfect example. We've got devices with totally different needs. A big LAN in Tokyo, a smaller network that needs maybe 45 hosts, and then this tiny little link between two routers that only needs 2 hosts. If we slapped a single /19 mask on this whole thing, we'd be wasting thousands upon thousands of addresses. This is the exact problem that VLSM was invented to solve.
All right, let's dig into the solution. VLSM is the efficiency tool that every serious network professional has in their back pocket. It lets us build a network architecture with real precision, with elegance, and with zero waste.
So what is VLSM, really? At its core, it's the process of subnetting a subnet. It sounds a bit weird, but it just means we can take a block of addresses and carve it up into pieces of all different sizes, perfectly matching what each part of our network actually needs. The result? No more wasted address space. It's beautiful.
Now, I know it might sound complicated, but the actual process is super logical if you just followed these steps. First, list out every network segment you need and how many hosts each one requires. Second, and this is the most important part, you sort that list from the largest requirement down to the smallest. Then, you just start assigning address blocks from the top of your list and work your way down.
Okay, time to put this into practice with our example network. We've listed and sorted all of our needs, and the biggest one by far is Tokyo LAN A. It needs 110 hosts. So to support 110 hosts, we need a block that can hold at least 126, and that means we need a /25 prefix.
So we give the very first available block, 192.168.1.0/25, to Tokyo. Done. That block uses up addresses all the way to .127. So what's next on our list? That would be Toronto LAN B, which needs 45 hosts. Starting at the very next available address, we assign it a /26 prefix. That gives it 62 usable addresses, a perfect fit with a little room to grow.
And we just keep going right down the list. The next network gets a /27, the one after that gets a /28, and that tiny link between the routers, it gets a /30. And look at that. Every single piece of our address space is accounted for. It's like a perfectly solved jigsaw puzzle. No gaps, no overlaps, and absolutely no waste. That right there is the power of VLSM.
So, you've seen the theory, you've seen it in practice. Now, how do you get really good at this? How do you make it second nature? It all comes down to one simple thing: practice.
Subnetting is a skill, and just like any other skill, you get better with repetition. You build that muscle memory. Here are 3 fantastic websites that are just packed with practice problems. Think of these as your personal training ground.
So instead of a quiz this time, I'm giving you a homework assignment. It's pretty simple. For the next 7 days, I want you to do at least one practice question from each of these 3 websites. That's it. Just 3 questions a day. If you do that, I promise you, this stuff will start to click in a whole new way.
And that brings us to the end. I want to leave you with this question. Now that you have this power of efficient network design in your hands, what's the first problem you would solve? Maybe it's your own home network, or the network at your office. The possibilities are everywhere. Hey, if you found this explainer helpful, hitting that like and subscribe button really does mean a lot. It helps us keep making more of these for you. Thanks so much for watching.